Okay, so we're going to continue in chapter 5, looking at the definite integral in this section 5-2. So we're going to first start by taking a look at what a definite integral is and what it calculates. We'll look into some properties of definite integrals, and then we'll take a look at like evaluating definite integrals as well. Okay, so to start with, if f is continuous and defined on the closed interval from a to b, then we say that the definite integral of f of x on that closed interval is going to be written like we have down here below. Okay, so when you see the symbol that looks like an S, that's our symbol for an integral. Okay, the number, so usually a and b are going to be numeric values. So the a value on bottom is going to be what's called the lower limit of integration. So that's going to be the starting point of our interval. The b value on top is going to be what's called the upper limit of integration. F of x is the function that we are integrating. And then dx, so the variable that you see there, x, that's the variable we are integrating. With respect to. Okay, so in this case, we're going to be integrating the function f of x with respect to the variable x. Okay, so there are a couple of things that we need to keep in mind in regards to definite integrals. Okay, when we evaluate a definite integral, that's going to be equal to a number of some sort. Okay, and what that number is going to represent, if you look down at number 2, that number is going to represent the area between your function f and the x-axis on the closed interval from a to b. Now, if you guys remember back in the previous section, we did approximation, so we used rectangles, the left, right, and midpoint Riemann sums, as well as the trapezoidal approximations. We use those to estimate area enclosed between our function and the x-axis. In this section and in subsequent sections, we're going to be calculating the exact area between a function and the x-axis. Now, in this section, we're going to be doing that with geometric shapes. So you're going to have like areas that correspond to triangles or rectangles or trapezoids or semicircles that you can use the area of geometric shapes to find the exact area. But we'll learn different techniques as we progress through chapter 5, which is going to allow us to find that area for any type of function. Okay, so let's continue. If f of x takes on positive and negative values on an interval, the net area, okay, enclosed by the function f of x and the x-axis between a and b can be expressed as follows. Okay, so I have some function y is equal to f of x that is positive on some part of the interval from a to b and is negative on some other part. Okay, so we have that positive area, which we're going to call a sub 1. That lies above the x-axis, and then we have the area that lies below the x-axis as a sub 2. So if I want to calculate the integral from a to b of f of x, which we are integrating with respect to x, then that area enclosed by the function and the x-axis is going to be equal to a sub 1 plus a sub 2. So we're going to sum up those two areas, but a sub 2, the area that lies below the x-axis, we're going to count that as a negative area. Okay, so area that lies above the x-axis will be positive. Area that lies below the x-axis is going to be counted as negative, which, I mean, if you think about it, like in terms of like the Riemann sums, that should make sense. If your area lies above the x-axis, the height is going to be positive. If the area lies below the x-axis, the height is going to be some negative quantity. Okay, next thing we're going to look at are properties of definite integrals. Okay, and I think we have 7 of these in total. Okay, so property 1 says if we take the integral from a to a of f of x, which we're integrating with respect to x. So if your lower limit of integration and the upper limit of integration are the same, then the value of that definite integral is going to be equal to 0. Property 2. If we take the integral from a to b of f of x plus or minus g of x, which we are integrating with respect to x, sorry for my son yelling in the background, that's going to be equal to the integral from a to b of the first function f of x, which we're integrating with respect to x, plus or minus the integral from a to b of the second function g of x, which we're integrating with respect to x. Okay, so if you have the sum or difference of 2 or more functions, you can separate that into taking the integral of each function and then adding or subtracting the results. Okay, number 3, if you have the integral from a to b of some constant c, which you're integrating with respect to x, that's going to be equal to c times b minus a. Let's take a look at why that's the case. Okay, so if we have some constant function c, then the graph of that function is going to be a horizontal line. If we integrate that function from a to b, the resulting shape that we get between that function and the x-axis is going to wind up being a rectangle. If we want to calculate the area of that rectangle, the length of the base is the length of our interval, which is b minus a. And the height of that rectangle is the value of the constant, which is c. So when we take base times height, that's b minus a, which is the base, times the height, which is c. Okay, property number 4. So property number 4 says if we take the integral from a to b of some coefficient c times a function f of x, which we're integrating with respect to x, I can take the coefficient c and pull it out front of the integral, and then I'm going to multiply c by the integral from a to b of f of x, which I'm integrating with respect to x. Okay, property 5. If we have the integral from a to b of f of x, which we're integrating with respect to x, we can switch the limits of integration. Okay, so typically when we integrate, we want the lower limit of integration to be the smaller number and the larger limit of integration, the larger value to be the upper limit of integration. But we can switch the limits of integration by taking the opposite of our integral. Okay, so again, if I have the integral from a to b of f of x, which I'm integrating with respect to x, I can switch the limits of integration by taking the opposite of the integral. Okay, property 6 says that if a is less than c, which is less than b, then the integral from a to b of f of x, which we're integrating with respect to x, is going to be equal to the integral from a to c of f of x plus the integral from c to b. Okay, so if I go back like up here with this diagram that I drew, if I said that the x-intercept of the function f of x occurred at c, then we can say that the integral from a to b is equal to the integral from a to c plus the integral from c to b. Okay, and then lastly, property number 7 says that if f is an odd function, then the integral from negative a to a of f of x, which we're integrating with respect to x, that is going to be equal to 0. Easiest way to illustrate this is if we had the function like y is equal to x. That's an odd function. If I took the integral from negative a to a, we know that odd functions have origin symmetry, so we should get an equal image. That's not drawn very well, but we should get an equal image on, like for example, in quadrant 1 and in quadrant 3. Well, the area, because the area in quadrant 1, because that lies above the x-axis, that area gets counted as positive. The area that lies below the x-axis gets counted as negative. Since those two areas are the same, that net area is going to wind up becoming 0. Again, because we have equal area both above and below the x-axis. Okay, so let's do a couple of examples then where we utilize the properties of definite integrals. All right, so for the first one, or the first set, we're told that the integral from 0 to 1 of x cubed, which we're integrating with respect to x, is 1/4. And then we're asked to find, in number 1, the integral from negative 1 to 1 of x cubed, which we're integrating with respect to x. So this should be a pretty easy one. When we look at x cubed, I know that x cubed is an odd function. So that just illustrates property number 7. If we take the integral from negative 1 to 1 of an odd function, that integral is going to wind up being equal to 0. Okay, when we do number 2, so for number 2, we have the integral from 0 to 1 of x cubed plus 3, which we're integrating with respect to x. So I want to use my properties of definite integrals to like rewrite that integral. So what I can do with 2 is I can rewrite that as the integral from 0 to 1 of x cubed, which I'm integrating with respect to x, plus the integral from 0 to 1 of 3, which I'm integrating with respect to x. Well, we're told that the integral from 0 to 1 of x cubed, we're told that that's equal to 1/4. If we want the integral from 0 to 1 of 3, again, that's going to wind up being a rectangle. The height of the rectangle is going to be the function value, which is 3. The length of the base of that rectangle is going to be our ending value minus our starting value. Okay, so that's 1/4 plus 3, which is 1/4 plus 12 over 4. That winds up being equal to 13 over 4. All right, we want to simplify number 3 as well. We're not going to be able to simplify number 3 completely, but we want to use our properties to do the best that we can with this. So what we can do to start with here is we can rewrite the quantity x over 2 cubed. I can apply that exponent of 3 to both the numerator and denominator. So that's going to be x cubed over 2 cubed, which is 8. And then I can take the coefficient 1 over 8 and pull that out front. So that's 1/8 times the integral from 0 to 2 of x cubed. And then I can take the integral from 0 to 2 and break that apart into the integral from 0 to 1 of x cubed plus the integral from 1 to 2 of x cubed. Right? And we know that the integral from 0 to 1 of x cubed, we're told that that is equal to 1/4. The integral from 1 to 2 of x cubed. You students who had Calc AB last year can do that, but the students who took pre-calc last year, like, we can't do that yet. So we're going to stop at this point. Like, that's as far as we can go simplifying this for the time being. Okay, so let me give you guys now like a test level example involving these properties. Okay, so I put this question on calculus tests in the past before. Okay, so this one says that if the integral from 1 to 5 of f of x, which we're integrating with respect to x, is 3a minus 11, and the integral from 1 to 12 of f of x, which we're integrating with respect to x, is 7a plus 15, then we're asked to find the value of a such that the integral from 12 to 5 of 2 times the function f of x, which we're integrating with respect to x, is equal to negative 82. Okay, I want you guys to give that one a try on your own. So pause the video, and then once you've completed, go ahead and restart it, and we'll take a look at the solution together. Okay, so let's go ahead and work through this example. So what I want to do is I want to get like an integral equation set up to start with here. Okay, so I know that if I take the integral from 1 to 5 of f of x, which I'm integrating with respect to x, and to that I add the integral from 5 to 12 of f of x, which I'm integrating with respect to x, then when I add those two integrals together, that should give me the integral from 1 to 12 of f of x, which I'm integrating with respect to x. Okay, so if I take that equation and I subtract this on both sides, then that's going to make the integral from 5 to 12 of f of x with respect to x equal to the integral from 1 to 12 of f of x, which I'm integrating with respect to x, minus the integral from 1 to 5 of f of x, which I'm integrating with respect to x. Okay, which will make the integral from 5 to 12 of f of x, which I'm integrating with respect to x. We know the integral from 1 to 12 is 7a plus 15. Minus, we know the integral from 1 to 5 is the quantity 3a minus 11. So that's going to make the integral from 5 to 12 of f of x. When I subtract those two, we get 4a plus 26. Okay, now we want to take this integral expression and work with it. Okay, so we have the integral from 12 to 5 of 2 times f of x, which we're integrating with respect to x, equal to negative 82. What I want to do is I want to take this integral here and make it look like that integral over there. Okay, so first thing I'm going to do is I'm going to take the coefficient 2 and pull it out front. Next thing I want to do is I want to switch the limits of integration. Okay, I want 12 to be the upper limit and 5 to be the lower limit. So the way I do that is by taking the opposite of the integral. So if I want to isolate that integral, I have to take my equation and divide both sides by 2. Divide by negative 2. So negative 82 divided by negative 2 is going to be 41. Okay, so once I know that that integral is equal to 41, I'm going to replace that integral over here with 41. And then when I solve for a, I'm going to subtract 26, which makes 4a equal 15, and a equal 15 over 4. All right, so that's a really good problem that utilizes several of the properties of definite integrals that we looked at earlier. Okay, we're going to finish the rest of the lesson up in the next video.